So
This
forgive me if
conference will now be recorded.
It's a new format for me, so please forgive me if I make a few errors along the way, but hopefully it'll run smoothly. Just to introduce myself again, my name is Julian Mason from Engineering Integration. I'm a director of the company, and as was stated earlier, we provide a consultancy service to the rail industry and also highways agency, etc. I'm talking today regarding heat straightening of impact damaged structures. But first of all, just like to give you a little bit of a insight into engineering integration itself. Engineering integration is a consultancy, and we provide specialist engineering services into the rail industry predominantly, and that is our core business. We provide CREs, CEMs, DPEs, PEs for both Network Rail and also the supply chain, and we've been doing that for the last 6 years, and we've grown and developed a successful business associated with that. There is other engineering elements of the business that we operate, and we have consultancy services undertaking feasibility studies for reopening railways. Obviously, that's a very popular topic at the moment, with all of the funding that is coming from central government associated with that. And also we provide safety assurance services as well to people like Transport for Wales, Network Rail, etc. So that's a very buoyant part of our business as well. So this is some of the projects that we're actually involved with at the moment. We're working for a selection of clients, private developers in Cardiff Parkway Station, Midland Metro. I won't read through them all, but there's a list of the projects that we're currently involved with. As you can see, we have various clients, including Network Rail, private developers, contractors, etc., etc. And we're very proud also to be working on the Commonwealth Games, the infrastructure construction element of that project within the West Midlands. So moving on to heat straightening and the topic that we're discussing today. Heat straightening, or this is a typical view of the underside of a rail bridge. As you can see, it's been struck numerous times by vehicles, which has caused the flanges, the bottom flanges of the girders to be distorted. And you can see there that there's quite significant damage, which is obviously affecting the strength carrying capacity or the carrying capacity of the bridge. When we look that into a little bit more detail, you can see there that we've actually got significant deformation of the bottom flanges. We believe that this structure was struck by a container being carried on the back of a lorry, and the container impact points are actually quite well defined on the structure, and you can see there that the bottom flange has rotated significantly. We'll come back to that particular structure in a little while, but I just wanted to give you an insight into the type of damage that we're actually dealing with. So heat straightening, the advantages of heat straightening are that it's most advantageous for realigning the main elements of the structure, so the main structural girders. It can be done in situ. There's no structural propping required to actually support the structure whilst we're undertaking the heat straightening, because we retain the majority of the permissible stress in the main girders whilst we're actually undertaking the heating. There's a very low number of operatives required during a heat straightening process. We would generally take 4 crew to site with a supervisor. Typical shift durations, so the typical duration of the project would be 2 to 3 shifts, depending on how many heat cycles would be required. When we're actually undertaking the works, if there are 2 damaged girders, we can alternate between the girders that we're heating. So we heat one, allow it to cool, and then we heat the next. So that makes us very efficient when we're actually working on site. We generally utilize MUPs to access the structures. Therefore, there's no extended road closures required beneath the structure when we're actually undertaking the operation. And also, there's no heavy plant and equipment required we just use hand tools to undertake the works. And I think most importantly, heat straightening costs are typically less than 10% of that of a replacement. So there's significant savings there, particularly when the infrastructure owner doesn't know who's caused the damage, because a lot of vehicles strike bridges and then drive away without reporting the incident. And it's obviously a very expensive process for the infrastructure operator to undertake steelwork repairs on these types of structures. So the principle of heat straightening is based on partially constraining the material during heating and then allowing it to cool unrestrained. And as it cools, it obviously contracts and therefore shrinks. So if you actually consider heat straightening in the context of actually heat shrinking, that's probably an easier principle to actually understand. So this is probably the most obvious way of actually describing how heat straightening works. Basically what we're doing there, you can see that there's a test piece in the middle of the diagram, and then there's a forged anvil, that sort of a clamp that sits around the test piece. When we heat the test piece, it can actually expand in only two directions, in the X and Y directions. And as it heats up, it obviously tries to expand, but it can't expand longitudinally. Therefore, as we allow the element to cool, it is able to cool in all three directions. Therefore, the steelwork effectively shrinks in the Z direction. And that's principally how we actually undertake heat straightening and the principles behind it. This is a typical diagram showing the reduction in permissible stress based on temperature. So obviously we don't want to heat the structure too far, because obviously we reduce the permissible stress significantly. Our target temperature, our critical temperature, is around about 650 degrees C. At that temperature, we are looking at a reduction in permissible stress or yield stress of around about 60%. That's if the whole section was heated up simultaneously. But we're actually applying heat to a very localized point. So we're not actually heating the whole cross section of the steel girder up simultaneously. We're just doing it at very discrete heat patterns. So that is limited. So the permissible stress is actually a lot higher than what is taken from that chart. So it's the average temperature of the section that we're actually looking at. We limit the critical temperature to 650 degrees C, because if we go above 650 degrees C, the crystalline structure of the steel starts to change, and it changes from body-centered carbon to, or body-centered crystalline structure to face-centered crystalline structure. That basically removes the or moves the carbon content around within the steelwork. If you then subsequently allow that steel to cool very quickly, some of that carbon can get trapped and become brittle, increase the carbon in certain, get crystalline carbon concentrations in certain areas that cause the steelwork to become brittle. So we want to avoid that. That's why we heat progressively and we cool progressively. So that's what we're doing to the permissible stress. The reason why we want to minimize the reduction in permissible stress is that we want to reduce the strength loss of the steel during the heating process. Therefore, we can effectively just remove the live load from the structure, and then that would probably accommodate the level of reduction in yield stress that we have. Heat straightening is very difficult to hot mechanical straightening. Hot mechanical straightening is where you actually heat the whole structure up till it's red hot, and then apply force to the structure and actually bend and push the structure back into shape. We don't actually do that with heat straightening. This is a typical example of a highways bridge that was hit by a low loader carrying an excavator, and the impact point there is quite obvious in the image, and the excavator arm struck the bridge and actually, as you can see, has displaced the bottom flange of the girder and distorted the web. Obviously, this is affecting the load carrying characteristics of that structure. So just looking in plan on the bottom flange, you can see there that there's the deflected shape, exaggerated deflected shape, and we have there's been an impact which has caused a lateral deformation of the bottom flange of in the order of 110 millimeters. Therefore, we have elastic deformation and plastic deformation occurring. The plastic deformation is the area where we want to actually apply heat and shrink the steelwork so we can actually restore the structure back to its original shape. The plastic deformation, as I said, is where we want to apply the heat, and that's where we want to provide the shortening, because that has gone beyond the elastic deformation and won't return to its original shape just by releasing the forces and what have you. So this is the elevation on the structure of the example given, and you can see there that the strike point is on the centre line of the eastbound carriageway, and the range of deformation is also shown there and depicted by the dimensions. As you will also appreciate, there is a to actually allow the deformation of the bottom flange to occur, there is a crease in the web of the structure as well, and which is depicted by the long line that actually dives down and then becomes horizontal again on the center line of the structure. The reason why that line dives down is because there is actually a lateral restraint at that point, that one of the bracing members within the bridge is actually positioned at that point, and obviously that is restraining the web and not allowing it to bend or have a fold line continually along the top chord of the web. When we talked about earlier about providing restraint, this is how we would typically provide restraint, and this is passive restraint, so we're not providing any jacking force in the prop. We're just basically putting enough force in the prop to actually hold it there. We then heat on the outer face of the deformed girder. That tries to push and rotate the girder towards the left as you're looking at the screen. Obviously it can't because of the prop, but as the girder cools, it can actually move away from the prop and the prop becomes loose. And that's principally the principle behind heat straightening and the restraint that we provide. So this is the operation being undertaken. As you can see, there's very little removal of paint that we've had to undertake to allow the heating process to be undertaken. The heating areas are we remove by blasting all of the paint within the proposed heating areas, and then we apply the heat using oxyacetylene torches. You can see there that we've actually used scaffolding in this instance for the operatives to actually gain access to the structure. This isn't ordinarily the case. It's just that the Highways Agency in this instance was able to give us full road closure. Therefore, it was most practical to actually provide scaffolding in this scenario. Just moving on to the next slide, you can see the heating patterns that have been applied to the steelwork. This is on the web. The center circle of the heat that's been applied is where the actual cross member is actually positioned on the opposite side of the girder to the view in the photograph. And therefore we actually apply heat in that and shrink the surface of the steelwork and actually restore the shape of the girder. This is typically some V-heat patterns that we would actually apply to the bottom flange of the girder, and you can see there that if you actually overlaid all of those heat cycles, you would get quite a concentrated set of V-heats applied to that bottom girder, and that's typically what we would do when you've got the deformation of this type. To look in more detail at the actual heating pattern associated with the V-heat, you can see there that the operative uses the arrows to follow and actually apply the heat in the girder, in like basically washing the girder from the web and working away to the edge of the flange. And you can see the concentration of heat there and you can see the patterns of heat and how the heat has been distributed into the girder. It's very key that we actually look at that and see the heating patterns, because that is what we use for actually controlling the temperature. We can't actually use thermometers because the process and the change in temperature is very quick. So we actually use heat patterns to actually identify the amount of heat that we've actually put into the girder. This is a test panel that we've undertaken, and you can see there that we've applied different heats to different sections of the girder. And you can see that the circumference of the circle is quite well defined within the steel. You can see there where we've overheated up to 900 degrees, you've got a very wide open dispersal of heat. Whereas when we're actually working at around about 650 degrees, which is our critical temperature, you can see that the circumference of the circles is quite tight, and you can see that we've actually assessed it and agreed that the critical temperature that we need for the heat straightening process is 45 millimeters, and that's depicted in the lines shown on the test piece. If we go over 650 degrees C, you can see the actual heating pattern extends outside of that 45 millimeters. What we do during trials, we actually take a test piece that has similar material properties and thickness to the girder that we're going to be straightening, and undertake heating trials on each element. And we use heating crayons to actually define the actual temperature of on the test panel. But we don't use heating crayons extensively when we're actually undertaking the works on site. We utilize the heating patterns that are actually shown on the steelwork. This is a graph showing the response that you get from the girder, and you can see that the top graph shows you the response you get initially, and then you get diminishing returns the more heat patterns you apply. So the top graph shows the first set of heating cycles, the first graph shows the original shape of the girder post impact, and then you can see that heating trials actually, as the heat is applied, the girder starts to move towards its original position. When you actually apply the first heating trials, you've got a lot of elastic response in the girder that's actually helping you. So as soon as you start to shrink the steel in the plastic zone, the elastic elements of the steel start to force the girder back into its original alignment. And then that elastic force reduces as you apply more heating patterns. And you can see there that we've continued heating patterns through. We've got up to 12 heating patterns that we've applied to that particular girder, and that will be a full heat and cool process during those application of those heating patterns. We have a target to hit to do with straightness tolerance. That is defined in BS 5400 Part 6. Basically, we apply heat until we get within those parameters, and that's theoretically what the steel would have been manufactured to when it was originally fabricated. So that's the target that we're actually looking for. And you can see there that this is actually the straightened girder in its final position once it's actually had all of the heating patterns applied to it. And you can see there is a slight deformation in the girder, but that is within fabrication tolerances. And if we were to apply lots more heating patterns, we may actually make that slightly better, but it's not critical. Therefore, we've taken it to a point where we feel that it's the most appropriate level and it's within the fabrication tolerances that are defined. These are some of the typical bridges that we've been asked to look at. You can see there that the one in the photograph on the left-hand side of the screen is where a vehicle has hit the bottom flange of the girder. Again, it's likely to be a construction vehicle on the back of a low loader to do that very sharp impact point. And then in the right-hand screen, you can also see that there's a significant amount of damage associated with an impact, and that's a girder that may be beyond the realms of heat straightening. However, it's likely that we'll be able to use a process of overplating or cutting out of the sections and butt welding in new sections of steel work and then using heat straightening to correct the alignment of the web, for example. We don't only do steelwork repairs or heat straightening on steel structures. This was a project in Brunei. This was a large gantry that the contractor was using to install precast concrete span sections. This gantry was used to lift up the precast concrete units, lift them into position and slide them onto the piers. Unfortunately, something went wrong and they managed to bend the gantry, and they rang us up and asked whether we could assist them with heat straightening the bent element of the temporary works without actually moving the gantry out of position. That is another shot of the slide of the gantry itself, and this is the bent section of temporary works that we were having to straighten. The red dotted line shows the where we were required to apply the heat. We applied the heat, and we were able to restore the shape of the distorted member. The contractor then went ahead and applied some more stiffeners around that connection, and they were able to continue working with the gantry. We were unaware at the time, but the gantry that was being built, or sorry, the structure that was being built in Brunei was actually 19 kilometers long, and they were on span 6 when they actually bent the temporary works. So they were very relieved that we were able to find a solution for them. So going back to the very first slide in the presentation, we look again at the typical railway structure that has been impacted. And you can see there that we've got 6 girders that have been impacted at different times. The impact points are actually almost 8 feet apart. So therefore, we're assuming that the impact point or the impact was caused by a container, the hard spots on a container being carried on a low loader. And obviously that's what we would be looking to restore the shape of using heat straightening. Other aspects that we would need to look for whilst doing our inspections would be tears in the bottom flange, and also brittle fractures, where there's been the impact has caused a brittle fracture. Obviously, we need to be aware of those, because if we start applying heat, we could exacerbate that problem. So we would probably have to cut that brittle fracture out, plate it before we started any heat straightening. So we're very conscious of any brittle fractures that occurs in the steelwork in and around the impact point or remote from the impact point. So again, I think we've shown that slide before. Therefore, you can see that the rotation of the girders and the respective strain ratios associated with the rotation of the girder. We in the UK are limited to allowing a strain ratio of 50. Anything above 50, the Highways Agency at the moment won't allow us to heat straighten above that point. So therefore, we're limited to an upper strain ratio of 50. In the United States, they've allowed contractors to take the strain ratio beyond 50, and they're working with strain ratios up above 150. So they're pushing the boundaries far more than we are doing in the UK. So we're taking quite a conservative approach at the moment, but we hope to do some more trials to allow us to understand whether we can actually take the strain ratios beyond 50 or deal with structures that have strain ratios beyond 50 within the UK, and demonstrate that through research and development. That would be the typical repair that we'd be looking for on this type of girder. Because of the extreme strain ratios that were shown in the earlier slide, we would limit, we would cut the bottom flange off effectively, and then we'd replace that with back-to-back angles, and we'd use heat straightening to straighten the web. So it'd be a combination of techniques to actually deliver the remediation. We also offer training opportunities, and we offer several courses to allow people to understand heat straightening more thoroughly. We offer a design appreciation course, bridge inspection course for bridge examiners to understand whether heat straightening is appropriate. And also we offer a course for inspection of surveying of structures So engineers can go out and actually survey the structure and pick up the salient information that we need to allow us to design a heating procedure to do any remediation works, etc. The courses are conducted on Microsoft Teams and will vary in length to suit the course content, but typically we would have probably 5 individual sessions, probably of the duration of approximately 2 hours. And that's the sort of training that we do to support the development and understanding of heat straightening. That's me done. Hopefully it was very interesting for you, and I'm open to take any questions that anybody has. So thank you very much for listening, and I look forward to your questions.
Right. Thank you very much, Julian. That was absolutely fascinating. Right. Have we any questions? If we can use the chat function, and we can come up with any questions. We haven't got anything yet. So I'll ask the first question, if I may, Julian.
Of course, yes, no problem at all.
Do you ever have, with this technique, do you ever have any problems with sort of redistribution of stresses in the girders?
There are, it's a very adaptable process, so we can predict what we think is going to happen. However, within the fabrication process or the rolling process of steel girders, you do get a lot of residual stress. So when we actually apply the first set of heating patterns, we may actually get movements that we're not expecting. But then what we have to do is redefine the heating process to understand what's actually happening, and actually then apply different stresses in that respect. But there are a lot of residual stresses within steel work, and we do get some movement of those stresses as we're applying the heating patterns.
Okay, thank you. Right, we've got a question from Andrew Wilson, and he's asking, is 650 the top temperature you use?
It is the top temperature that we would use, because if we go beyond 650 degrees C, we start changing the crystalline structure then, and anybody who's into their metallurgy, the carbon starts to come out of the crystalline structure at 650 degrees C, and if it's not allowed to cool very slowly, you can actually get carbon embrittlement within the steel, and therefore that obviously is not something we want, because obviously the steel becomes more brittle and we can get brittle fractures occurring and what have you. So we do limit it to 650 degrees C because that is considered to be our critical temperature. I think the actual temperature where crystalline structure starts to change is about 720 degrees C, but it's we use the 70 degree margin to actually ensure that we've got a level of a tolerance, just in case there is any particular areas which are marginally overheated. I hope that
thank you.
answers your question, Andy.
Do you reheat to the always to the same temperature, or do you reheat to a lower temperature? Is it always to 650?
We always try and work to 650 because obviously that gets the increased response from the steelwork. So it's balancing the two really. Between each heat cycle, we allow the temperature to come back down to actually ambient temperature before we apply the next heating cycle. And again, we get the most response from the steelwork by doing that.
Okay, right, we've got a couple more questions come in. So Simon Thomas says, how strong is the straightened area compared to the original component? For example, if it was re-hit, how would it perform?
The steel, theoretically, the steel is maintained its original yield strength. So we don't actually cause any reduction in yield strength by application of the heat. However, there is a limitation. The Highways Agency are limited to reapplication of heat for 2 consecutive times. So we basically limit the number of times that the heat straightening can be applied to a structure to 2. So obviously, once we've applied heating patterns to a particular area on a bridge, we would have the health and safety files updated so everybody knew where heating patterns were applied, and we could only apply heat once more to that particular structure before we could actually say, well, we need to do something different. We aren't able to use heat straightening again. Unfortunately, low loaders and what have you vehicles always hit the structure in the same place. It's usually on the centre line of the slow lane of a carriageway, either a motorway, dual carriageway, or a typical 2-lane highway. So it's usually on the centre line of the slow lane, and obviously the impact point is ordinarily there. So what we would advise is, once we've actually undertaken heat straightening, is that we actually provide some mitigation measures to try and stop that structure being struck again, by either warning signs, signage, or collision beams or whatever. But it's hopefully we can. The main cost would be mitigating the requirement to reconstruct a bridge, and then obviously that would be the main saving to the infrastructure operator.
Okay, thank you very much. Right, we have a question from Matthew Taylor. So thanks for the excellent presentation, Julian. How do you control the temperature levels during the heating?
Well, I think I don't know if, can everybody still see my slides or not?
Yeah, they're still up there at the moment. Yep.
Yeah. So if I just go back a couple of slides.
Okay.
Just bear with 1 moment. So controlling the heat during application. So you can see there that we've actually undertaken some heating trials on a test piece. So we're actually using the heating patterns to actually define what temperature the steel has been heated to. So we take a test panel that is the same thickness and same material grade as the structure, and we apply heats to it. And you can see there that we've applied a series of heats, increasing in temperature. And we've actually identified that at 650 degrees, there will be a circular heating pattern of 45 millimeters. And we use wax crayons effectively that melt at different temperatures. And you can see there's a blemish within the center of each of the heating patterns. So therefore we put these crayons on, and they have different categories of heat. So if we've got a crayon that's defined to have 650 degrees category, we apply the stick on the center of the heating pattern, and if it melts, it's above 650 degrees C. If it's lower than that, it's obviously below. So we can actually define the heat that we're actually putting into the structure by the circumference of the heating pattern that we've got. And you can see there at the top of the image, we've got some temperatures where we've taken it up to 900 degrees C. Obviously this is a test panel, not a final element or within a bridge structure. And you can see there the heating pattern is probably, I don't know, 120 millimeters, 130 millimeters in diameter. And you can see there it's obviously excessive heat has been applied at that particular location. So we use those heating patterns to define the heat that's been applied into the structure. We've tried using laser thermometers and what have you, but they tend to be very susceptible to the surface condition of the steelwork and give us very arbitrary readings depending on the surface condition. We have used them in the past, but our preference is to use heating patterns. Also, when we're actually heating, obviously the heat at the head of the torch is about 3000 degrees C, and you can appreciate that there's a lot of dispersal of heat occurring as you're applying the heat into the structure. So therefore, if you were using a thermometer or a temper stick to actually define it in practice, as soon as you take the torch away, the temperature probably drops instantaneously about 200 degrees C. So you're probably getting false readings. And if you're using temper sticks, you may actually overheat the structure inadvertently by the fact that a lot of heat has been lost out of the temperature, out of the steelwork as soon as you move the torch away from it. So our preference is to utilize heating patterns to define the heat. And I think the previous slide shows there a typical V heat that has been applied to a structure. And you can see there that we've actually put guidance lines on there using heat resistant chalk. And that basically gives the operator an idea of how much heat he's actually putting into the structure. It sounds quite basic, but it's very, very effective, I can assure you. Thank you very much.
Thank you, Julian. Right. Yeah, another question, Tim Thorne. To what extent is heat straightening being adopted by Network Rail, or is it just Highways England in the UK so far?
We've done about 30 structures, or 30 structures have been undertaken. We've probably undertaken about 3/4 of those within the UK, and they've been predominantly highway structures. Network Rail hasn't quite bought into this process yet, and we're very keen for Network Rail to adopt it, because we see significant changes or significant savings that can be justified by this type of process. Obviously, railway structures are significantly different in design, and we have undertaken a site survey at Limply Stoke on a bridge that has been struck, and we've identified that we can't rectify the damage completely by heat straightening, because of the certain elements of restraint and tears within the bottom flanges, etc. So we've recommended that there is a cutout, some cutouts required for that particular structure, and we can replace elements and straighten those elements, and then use heat straightening as a secondary activity. Also, the structure is obviously is quite old, probably built in the early 1900s, and there's a significant amount of corrosion. Obviously, we can't rectify corrosion section loss with heat straightening, unfortunately.
If only.
If only, that's right, yes. So where we've got significant section loss, obviously, we need to go back to traditional overplating methods of repair rather than using heat straightening.
Thank you very much. Right, question from Andy Packham. Is there thought to be any reduction of the residual fatigue life?
There is a marginal reduction in the residual fatigue life of the structure, and that's one of the reasons why the Highways Agency at the moment are limiting the process to only 2 cycles of heat straightening on any one particular section of a bridge. Obviously, if the bridge is impacted in different places and we aren't overlaying heating patterns, it's not as much of an issue. But what I'd like to do probably, Andy, is respond to that question more formally in a written response, maybe to the group, just to give you a bit more clarity on that, rather than just a verbal response, if that's okay.
Okay, if you pass it on, we can make that available to everyone. Right.
Yep,
Next
okay.
question is from Arvid Sedraval. Do you ever use the stiffness of the structure itself to constrain the component during heating, or is it additional constraints always needed?
We can actually use the mass of the steel structure depending on how it's actually supported, because in the fabrication process, where we want a planned curve in a particular girder, we can actually use the dead weight of the girder effectively to restrain it, because obviously as you apply heat, the girder won't rise up if it's being restrained by the weight of the girder itself. But it is very difficult, obviously, to use the stiffness of the girder to restrain it. But there is a certain element of that when we're actually undertaking the works. But ordinarily, we would provide passive secondary restraint during the heating operation.
Thank you. Right, one from Jeremy Rees. Are there any non-bridge applications for this process? For example, impact damage in ships?
It's used extensively in the fabrication industry and shipbuilding to take out weld distortion. So therefore, yes, it could be applied to impact damage, any type of impact damage on a steel structure. There was one example that was used, one example I can give of a structure that was heat straightened. A contractor had put up a new bridge adjacent to an existing bridge, which it was my former employer, Fairfield Maybe, had provided the steel work for this particular new bridge. The contractor put all the new steel work up and then demolished the adjacent structure using explosives. I think he was a little bit overzealous with his explosives, and he managed to distort 11 of the newly installed girders. He came back to Fairfield maybe and asked what was the program cycle for replacing all of the girders, because he bent them all. And we said, no, you don't have to replace them all. We can heat straighten them. And we were able to heat straighten them in situ, obviously at significantly reduced cost. So there is lots of applications where we can use heat straightening. And my advice would be, if you have a scenario and you think you can remediate damage or remediate distortion using heat straightening, don't hesitate to give us a call or contact us via our website, and we can advise on what we can actually do. I think a primary example is the lifting gantry in Brunei, and where the contractor actually overstressed the gantry and distorted it, and the downtime and cost of actually repairing that structure traditionally would have been excessive. So they chose to contact us, and we were able to help them, and at quite minimal cost, and allowing the gantry to stay in position and not having to move it back to the mainland. So there's lots and lots of applications, and what I can advise is you just contact us and we can talk through the issue and hopefully give you some advice, and maybe use heat straightening if it's appropriate.
Right, we've got a few more questions. So Brinley Cox says, can heat straightening be undertaken on rail underbridges with trains still running?
We would have to look at it, and we would have to consider it very carefully. I would suggest it's unlikely, because we tend to use the live loading on the structure to be the differentiator to allow the slight reduction in permissible or the yield stress whilst we're actually undertaking the strengthening works. So our initial response is to always remove the live load, because that gives us the margin that we require to allow the slight reduction in yield stress. But I would like to take it on a case-by-case basis, and we could actually have a look at it. Perhaps we could divert onto an adjacent line and remove the immediate live loading from the structure, and that may give us enough to actually allow the works to be undertaken.
Okay. Right, another one from Arvid Sedraval. Is the limitation on repeated heat straightening on the same area due to grain growth of the steel?
Not that I'm aware, but what I would like to do is have a look at that in the context of reduction in brittle fracture and
the fatigue life, yeah.
Fatigue life of the structure, sorry. Yeah, and answer that question remotely if that's possible.
Okay. So we've got a question from Marco Aquati. Is heat straightening effectiveness depending on the season, i.e. is it less effective in winter?
We probably find it actually could be more effective in winter, because of the relative temperature difference that we're looking at. So it does have a marginal effect, but obviously what we tend to do is undertake these works at night. So the climatic temperatures are quite significantly reduced at night. So we don't see a significant change in the response on the steelwork depending on seasonal change, no.
Okay, thank you. Right, Brian Bell asks, most metallic railway bridges are made out of wrought iron. What development work have you done in relation to this material?
Unfortunately, heat straightening doesn't work on wrought iron, because there's lots of inclusions within wrought iron, and you don't get to the required transfer of heat through wrought iron as effectively as you do in structural steelwork. So unfortunately, we can't actually heat straighten wrought iron bridges or cast iron bridges. We are limited to structural steel bridges, unfortunately.
Right. Are there any more questions? All right, there's nothing else coming up. So thank you for an excellent presentation. I'd like to call upon Brinley Cox to propose a vote of thanks.
Can you hear me now, everybody? Yeah, is that okay?
I can hear you now. Thank you, Brinley.
Okay. Jason, thank you for a really, Julian, sorry.
Yes.
I'm an old git. My memory for names and faces is terrible.
It's good to hear from you, Brittle. I haven't seen you for a while.
No, that was a really interesting talk, actually, especially the Brunei incident. You must have saved their bacon there, although they don't have bacon over there, I don't think.
No, that's right.
And I think
they were very appreciative of our time, and they didn't show us the full extent of our of the issue when they actually first sent the problem to us. So I think we probably adjusted our fee slightly to associate the enormity of their problem, but we didn't have the opportunity, unfortunately. So I think we charged them £3,000 for consultancy services on that one. So I think they got off quite lightly.
Yes, it sounds like it. I think there is a lot of potential for this use on the railways, and I don't know if we've got any structures asset engineers in the audience, but if not, I recommend that you do your best to try and get Network Rail to rethink their policies. Very slow to change Network Rail, I think, like the oil tanker. You got to tell them 3 days before they got a turn. But thank you very much indeed. And if everybody unmutes their thing, we can say thank you in the traditional fashion. Do we do this, Andy? Can we all just clap?
Yeah.
Okay. Thank you very much.
Thank you very much. Thank you very much for giving me the opportunity to speak. And as I say, if anybody has any queries or would like to explore any opportunities for using heat straightening or the application of heat straightening, please don't hesitate to give us a call.
Okay, right. Thank you very much indeed, Julian. Right, and just before I draw the meeting to a close, just to future meetings for or some section news just before we finish. We've got our future meetings are coming up on September the 14th, which will be the section AGM, and then followed by a talk from Craig Havard, who's the gauging engineer, and he's going to be talking about RELA, which is the Rail Infrastructure Alignment Acquisition tool, which we're now using for doing gauging, and particularly in Wales Road. On October the 12th, we have our deferred talk from Colin Brading about the infrastructure asset transfer for the South Wales Metro. We haven't got a speaker yet for November, but the December meeting on the 14th of December will be Tim Kendall talking about tram train. So just to let you know, at the moment, we intend to get back in Cardiff when we have the opportunity. But clearly Network Rail's offices are not welcoming visitors at the moment. But alternatively, we'll continue in this format for the foreseeable future. And I suspect it'll certainly be for the rest of this year, but maybe next year we'll get back into a face-to-face meeting as well. So, okay. Are there any other issues anyone wants to raise before I call the meeting to a close? No? Okay, thank you very much. I'll have a quick chat with Andrew before he finishes. But, all right, I declare the meeting closed. Yep. Thank you.